Okay, this is our last video. Today's meeting was terrific. There were really interesting talks, industrial physics, people doing all kinds of interesting things there. Um, Radiation disrupting quantum computer chips. Really interesting discussion, interesting projects there. There was a terrific session on biophysics that we have to do something like that. That's just great. So tonight we're going to talk about circuit building. And let me pick up where we were. We talked about Ohm's law and resistors. And you'll remember that V equals IR is Ohm's law. And that describes how the voltage pushes a current through a resistor. So we had a little kind of baby circuit. We had a resistor and an EMF, and we wrote that the EMF is the voltage on the battery, and that was equal to IR. So the current in the circuit was just E over R. We also learned that series resistors add. So R equivalent is the sum of all the resistors, just add them up. And parallel resistors add as reciprocals. One over R equivalent is the sum of 1 over Ri. We also talk about power, I squared R. So we're really ready now to build circuits, and this is really some of the material that people really like a lot. It's the basis for a lot of electrical engineering and a lot of circuit design and a lot of experimental physics and electronic engineering and so on. And it really comes from two big ideas. The big ideas are known together as Kirchoff's laws. So these are two fundamental laws that describe circuits no matter what. They are always true because they represent two fundamental conservation laws. So on the exam that includes this material, I'll ask you to write Kirchoff's law. So it'll be on the practice test and it'll be on the real test. And I'll ask it again on the final. It's that important. So what are Kirchoff's laws? Well, the first one is that the sum of the voltages around any closed loop in a circuit equals 0. So this is really a statement of energy conservation. You can't go around a loop with an electron and pick up energy for free, because you could just keep going around and get lots of free energy. That's not allowed. So the sum of the voltages around any closed loop in a circuit must be 0. And that has to be true. If it isn't true, if you were to discover something that a circuit, if you could build a circuit that didn't do that, well, probably you'd be wrong. If you weren't wrong, we'd have to rewrite everything, because this is so fundamental. It's conservation of energy. The second of Kirchoff's laws is that the net flow of current into a junction is equal to the net flow of current out of a junction. So this is really a statement of conservation of charge. The charge can't disappear. It can't appear from nowhere. Charge is conserved. So these two laws, Kirchoff's laws, which are extremely fundamental ideas in physics and really the basis for um, everything really in electrical engineering. These two fundamental laws are really fundamental because they're fundamental principles of physics. So if you take circuit analysis, physics, or engineering 210, using Kirchhoff's laws is a large part of that course because you're going to use them and become more and more sophisticated. So to use these laws, we need to, especially number one, we need to define a convention for how we assign pluses and minuses to voltages. So we need a sign convention. So if we're going to sum voltages around any closed loop, we have to know which voltages are positive and which voltages are negative. So let me draw a little example of a circuit, and then we'll talk about the sign convention. So let's use our simple, kind of circuit we had before, our EMF or battery, and then we'll put a couple resistors in, like so. We'll call this R1 and R2. And of course, you could replace those series resistors. They have the same current. You could replace those series resistors with a single resistor if you wanted, but here I'm going to leave it that way so I can demonstrate what we're doing. So when I have a problem like this, I have to do a few things. I have to guess the current or currents. So in this case, I'm going to say, well, I'm going to guess a current that goes like that. So I have to guess both the current magnitude and direction, and I'm going to indicate it with an arrow. That's showing the flow of the current. And you're going to say, well, how do you know? And I'm going to say it doesn't matter. If I guess the current direction and I calculate it and it comes out to be positive, that means it's flowing in the direction I guess. If it comes out to be a negative current, it means it's flowing the opposite direction. So what matters is that you guess a current and you stick to the guess, not what the guess is. So guess the current, and in this case, there's only one current. In more complicated circuits, we'll have to label the currents. The second thing we need to do is to pick a starting point and an analysis direction. So what we're going to say we're going to do is we're going to analyze the circuit, and that means to find the voltages of the currents. So I often pick a point in the lower left-hand corner. It doesn't matter where you start. And I pick a direction for my loop to go around the circuit to a closed loop. And here there's only one loop, so here's my loop. Okay, and you're going to say, well, why'd you pick that loop? And the answer is I could pick a different loop. I could go the opposite direction. It doesn't matter because we're going to follow this sign convention. Okay, so you have to guess the currents, label them, and then pick a starting point and identify as many loops as you need. Okay, so now let's talk about the sign convention. So the sign convention means we have to assign pluses and minuses to the voltages across each of the components. In this case, it's across the E, across the R1, and across the R2. Okay, so what is the convention? So I'm going to go to the next page to write it. Okay, so the sign convention. First, if your analysis path crosses a resistor in the same direction as the current flows through the resistor, V equals minus IR. So this is just a convention. By the way, if you know how to do circuit analysis already and you have a particular convention you can continue to use that convention. But probably you don't. So this is the convention we're going to use. Why are we going to use this? Because in 1980, my physics professor, Neil Kayson, used this circuit convention. And so now, we're going to use this circuit convention, and 25 or 30 years from now, you're going to use this convention because this is where you learned it. And it doesn't matter which convention you use, but you have to pick one. So we're picking one. Okay, so number 2. If your analysis path crosses a resistor in the opposite direction. And yes, there's a hospital across the street from the hotel. So every time there's an accident or something happens, there's sirens. So if your analysis path crosses a resistor in the opposite direction as the current flows, through the resistor, well, you can guess what's going to happen is V equals plus IR. Okay. So the circuits we're going to analyze are really only going to have resistors and batteries in them. So we really just have 3 if the analysis path crosses the EMF from the minus side, which is the short side, short line side, in the symbol, to the plus side, which is the long side, the long line, V equals plus E. And finally, 4, if the analysis path crosses the EMF from the plus side, which is long, to the minus side, which is short, V equals minus E. Okay, so this is the sign convention. It's so important that I'm going to ask you to write it on the test, on the practice test, on the final. This is like 4 easy points, right? Just being able to write this. There's nothing to it. Just be able to write it down. So let's take our circuit now and let's try it. So we're going to go back. I'm going to go back in the page, right? And I'm going to say, well, I'm going to start here in this lower left-hand corner, and I'm going to go around the circle. So I'm going to go around the circle, and I'm going to cross the EMF from the short side to the long side. So short side to long side is going to be plus E. Go around here, I cross the resistor in the same direction as the current is flowing through the resistor. So again, my path is like this. I'm crossing that R1 in the same direction as the current. So that's going to be minus I R1. I'm going to now cross resistor 2 in the same direction as current's going through it. Minus I R2. I come back to the beginning. 0. That's Kirchoff's first law. Now, you could do a little algebra here. You could say, well, E is E minus I R1 plus R2 equals 0. And you could solve for the current. I is E over R1 plus R2. So you've now done your first circuit problem. Okay. Okay, so let's go back. We've got our sign convention here, right? Analysis path crosses the resistor in the same direction as the current flows. V equals minus IR. If it's in the opposite direction as the current flows, V is plus IR. If you cross the battery from the short side to the long side, it's plus E. From the long side to the short side, it's minus E. Let's do another problem. This one's going to have a junction in it. So another problem. A fancier problem. Okay. So let's put a battery in. Okay. And let's put resistor 1, resistor 2, and an EMF. Okay. So this circuit has both, we're going to have to apply the loop rule. We're also going to have to apply a junction rule. Okay. So let me see. I'm going to label a current here. We'll call this current I. There's a junction there, right there. We'll put a hard dot there. And there's going to be a I1 and an I2. So the current's coming in here and it's splitting at that junction. Okay. So I'm going to have to identify a couple loops, and I'll use the junction rule. So there are 3 unknowns, I1, I2. So we're going to need some combination, okay, of loops and junction rules, but we're going to need 3 conditions. So I'm going to say, well, we'll call that one loop 1. Okay, we'll call this loop 2, and then we'll look at that junction. Okay, all these problems look alike, right? So you assign the currents, you guess the currents. It doesn't matter what you guess. You just stick to it once you've guessed it. You pick some loops, you identify some junctions. So let's look at loop 1. Okay, so we're starting here in this lower left-hand corner. So I'm going to go around the loop. I'm going to cross the E. And cross the E. So from short side, that's the short side. Long, short, long, right? This is minus and plus. Okay, short side to long side, plus E. Go around the loop. I don't see any voltage changes until I cross the resistor R1. So it's minus I1 R1 equals, go back to the beginning, 0. So that's loop 1. Loop 2. So start here, go around the loop. So here I go, I'm going to go up this way. I'm crossing resistor 1 in the opposite direction as the current is going through it. So I'm going to write that as plus I1 R1. And then I'm going to go around the loop here, and the current going through 2 is I2, and I'm going the same direction as the 2, so it's going to be minus I2 R2 equals 0. And then finally, I have a junction here. So the junction rule tells us that the current going in is I, and so this is current in, and the current going out is I1 plus I2. Okay. Okay. So how would we solve it? So now we have to do some algebra. Solve. Okay, well, this one is actually pretty nice because this equation right here, that one right there, I can just solve that, and I can say, well, I1 is just E over R1. So I could compute that if I knew E and R. And typically you would know E and R. So with values. Okay. So then I could say, well, I now know I1, so I could say, well, I2 R2 is I1 R1, right? So that's that. So I2 is I1 R1 over R2. Okay. Okay. And now that I know I1 and I2, I could find I is just I1 plus I2. Okay. So this is like every problem, by the way. Every problem you're going to do the same thing. You're going to have, some batteries, voltage sources, EMFs. You're going to have some currents, some resistors. You're going to label things. You're going to apply the loop rule, apply the junction rule, and solve. So, this section right here, let me get my little highlighter here. This section here, okay, that's the physics, the highlight. That's the physics. The rest is algebra. That's the physics. That's what most of your work is going to be, is figuring out how to write the loops. Welcome to engineering, electrical engineering 101, which is really physics 2, applying the Kirchoff's laws. Now, let's do another example, and then we're going to call it quits for tonight, because I'm pretty beat up after a long day, really wonderful talks, but exhausting. Okay, let's do another problem. Okay, so this one's going to be a little more challenging. Okay, just because I wanted to do something a little more challenging, and we're going to set it up. We're not going to solve it right now. So let's say we have a battery, resistor, another resistor, oops, another battery. We're actually going to build this circuit in lab. Not this week, but we will. So we could have, let's say, E1 and E2, and an R1, an R2, and maybe an R3. Okay. So what do we have? We have let's call this current I1, We'll call this current I2. We'll call that current I3. And could I have drawn the currents differently? Of course, but I picked those. Okay, and so I have a junction here. So I'm going to have, let's see, I'll have a loop like this. That's loop 1. I'll do a loop like that. That's loop 2. And then we have this junction here. Okay. All right, so let's write loop 1. So we're going to start in the lower left-hand corner. We're going to go around the loop, right? So it's plus E1 minus I1 R1 minus I3 R3 equals 0. So that's going around this loop, and I use the current that's going through that actual resistor. Okay, let's look at loop 2. So I'm going to start in the lower right-hand corner, lower left-hand corner. Okay, so I'm now going to go against the current through I3, so that's plus I3 R3. I'm going against the current here, plus I2 R2. I'm going from the long side to the short side, minus E2 equals 0. So, right, I crossed against the current here, so it's plus. I crossed against the current here, it's plus. I went from the high side, the plus side, to the minus side, that's minus. Okay, that's loop 2. And then the junction rule. The junction is I1 plus I2. Those are incoming, entering the junction. They're pointing in, equals I3 exiting. Okay, so these are the 3 equations that you would need to solve. You have 3 equations. Three unknowns. Now you can imagine that what will happen is, as you get more and more complicated circuits, where you have more and more currents, this could get, really out of hand algebraically, right? You could have, thousands of currents to solve for. So you would probably do this with a tool, but you really do need to know how to do it by hand. I think the largest one I've ever done was an infamous problem that the instructor gave when I was at Notre Dame that was, I think, 7 unknowns, and you had to use some matrix technique for solving it. The electric circuits course, the 210 course, is being able to do fancier and fancier circuits that there's some powerful techniques for. If you're clever about it, you'll recognize those techniques when you take that class as being very similar to techniques that you're doing in statics, if you're taking statics. Okay, so let's summarize and we'll be done for tonight. Okay, so our summary. So you should know Kirchoff's, let's try again. Kirchoff's laws, which are really conservation of energy, conservation of charge, and then the sign convention. Okay, and the process is guess and label the currents, pick loops and junctions, and the sum of the two must, the number of equations you get must equal the number of currents. And you need independent equations, which is you have to think a little bit about, okay? And then apply Kirchoff's laws to the loops and junctions and solve. Welcome to circuits. So we'll do circuits that are, more complicated than a single loop, but we'll try to keep the algebra manageable. Okay, so that's our work for tonight, and I'll send it off to you, and I'll be back. I'm traveling tomorrow. I'll be back tomorrow night, and I'll see you all on Monday. I'll be in my office on Sunday afternoon after 3:30 too. So, okay, I'll see you all soon.